Hi everybody, Mrs. Pesic here.
And Miss Bella here.
And we are looking at section 6.3, piecewise functions. And the objective for this section is to write and graph piecewise functions and to use piecewise functions to describe real-world situations. So our vocabulary, piecewise function and step function. So what is a piecewise function? It is a function that is a combination of one or more functions, and the rule for a piecewise function is different for the different parts or pieces of the domain. So for example, a piecewise function might be linear at some point and end right here and then turn into a parabola at another point. So you would need two pieces to describe that function. So the function itself would be written in two pieces. Some function here for something, some function here for something.
So a real-world application of movie ticket prices are often different for different age groups. So the function for movie ticket prices would assign a different value or ticket price for each domain interval or age group. Now when we are going to write these, we're going to remember how to use interval notation. Square brackets indicate an included endpoint, and parentheses indicate an excluded endpoint. Or whenever we use infinities, we always want to use parentheses as well. Alright, so our first example here is it's a consumer application problem, and we're going to start off, the given information here you would have would be this table. So we're given the weight and the price per pound, and we're giving three pieces of the graph here. So it's piecewise because it's described by more than one function. So we're going to create a table to kind of demonstrate what's happening here.
It pays to buy in bulk, Miss Bella.
It does. The more you buy, the cheaper it is. So because the endpoints of each segment of the graph identify the intervals of the domain, we're going to use the endpoints and points close to them as the domain values in the table. So again, what that's telling you is, when is my graph changing? Well, this piece is changing when my x value is 2. And then I have this next part between 2 and 4. And then this one picks up right here from, or maybe about 5 I should say, about from 5 so on our table. So we want to have three different pieces of information or domains to describe what's happening. So let's create our table here. Well, what was the first piece of our graph we were given? If the weight was between 0 and 2, then how much price per pound was I paying? Well, that was that top piece right here. I was paying $8 per pound. So that's the first piece we put on our table there. Whoops, I highlighted it on accident. So we're going to say up to 1.99 pound because you notice an open circle here, so not quite at 2 pounds. My next part of the table, well, when it's now 2 pounds, a closed circle, all the way up to whatever this x value here would be. So I'm going to say that's about 5. And again, it's open circle, so maybe really, really close to 5. Oh, that's my mistake there using a highlighter. So 4.99. Now my price is $6 per pound. And finally, from 5 pounds and higher, I'm going to pay $5 per pound.
Okay, so at this point we are going to want to write a verbal description. So the verbal description could be that mixed nuts cost $8 per pound if you're going to buy less than 2 pounds, $6 per pound if you're going to buy 2 pounds or more but less than 5 pounds, and $5 per pound if you're going to buy 5 or more pounds. So that's the verbal description that would go along with this table and also go along with the graph. And at this point we're not writing an equation for this, or no? Moving on then. All right, so your first notes must do, you are going to create a table and a verbal description to represent this graph. This is regarding the green fees at a golf course. So just so you notice, you're going to write your own, you're going to make your own table of values. That would be the the time here and the fee that you have to pay here, and you're also going to have a verbal description that you're going to write. All right, and you should probably notice that this is going up by 3, so this is probably 24, 27. I think that's right about 28, if that helps you get your table and your verbal description.
Now, when we take a look at piecewise functions, sometimes we'll notice that it's a constant value. So in this example, we have that our function is 5 if x is between 0 and 13. Or our function is 9 if 13 is less than or equal to x, which is less than 55, and 6.5 if x is greater than 55. So each of those are a constant. So a piecewise function that is constant for each interval of its domain, such as ticket price function, we call that a step function because it almost looks like stair steps. It's going up, a step at a time. So maybe you want to do a little picture of what that would look like?
So is that an example?
Oh yeah, that would be perfect. That would be one that is going up at a constant rate, or is constant during that domain, I should say.
So that's an example of a step function?
That would be, even the one we did before, that was a step function as well. That also is a step function. So in order to read this, we have proper notation. We know how to read what we have written there. The way we would read that rule up above would be f of x is 5 if x is greater than 0 and less than 13, 9 if x is greater than or equal to 13 and less than 55, and 6.5 if x is greater than or equal to 55. When I want to evaluate, so evaluate means get a value, a number for it. I'm going to find the interval of the domain that contains, I'm looking right here, contains that input. So what number am I trying to evaluate? And then use that specific rule. So for this example here, let's say if I wanted to know when x is 15, what is f of x? Well, I would notice that 15 falls within this domain between 13 and 55. So I would use whatever this rule is. So in that case, this would equal 9.
Okay, so f of 15 is equal to 9. What about something like f of 6? What's f of 6 going to be?
Well, f of 6, what rule would that go with? That looks like it's going to go with the top ones between 0 and 13. So I would use that top rule. So f of 6 would equal 5.
5. All right, so let's try a few more of those. We're evaluating each piecewise function for x equals -1 and x equals 4. So let's take a look. What is h of -1 going to equal? Well, before we decide which of these two functions we're going to use, we have to decide, is -1 in this interval or is it in this interval? And since -1 is less than or equal to 2, we're going to use that first interval and that top function. So we're going to do 2 times -1 plus 1. That's a -2 plus 1, and we get -1. So h of -1 is equal to -1. And for this function here, if we're going to find g of, oh, I should go back. All right, g of -1 here. For g of -1, which one do we use? Well, -1 is less than or equal to -1. That's true. -1's not greater than -1. So we're going to use this function, and so we'll get 2 to the -1, which you know is 1 over 2 to the positive 1, and we get 1/2. So g of -1 is equal to 1/2.
Now, let's evaluate each of those for x equals 4. So our next part here. Again, before I can figure out what h of 4 is equal to, I need to decide if 4 is less than or equal to 2 or greater than 2. Hopefully we're okay with saying it is greater than 2, so I'll use this bottom rule. So h of 4 will equal the quantity of 4 squared minus 4. Or 16 minus 4, we get a 12 here. So h of 4 is equal to 12. As far as g of x goes, again, we're going to evaluate this at 4. So g of 4, we're going to look at our rules and say, is 4 less than or equal to -1 or greater than -1? It's going to be this bottom. So we'll use the rule of 5x. So this would be 5 times 4, or 20. So g of 4 is equal to 20.
So, Ms. Bella, do we now divide both sides by 4 to get g equals 5?
We do not. Remember, that's just a way to write the notation where we get both the x and y coordinate at the same time. So this is really telling us, so we don't want to do that. This is just telling us the point 420 is on the graph of g of x.
And g is not a variable, right? It's just the name of a function, so we don't want to solve for g. So yeah, that's no good. Okay, so that brings up notes must do for you. Notes must do number 2. You're evaluating this piecewise function for x equals -1 and x equals 3. So if there are 3 different equations or 3 different functions, Will they get 3 different answers for each of these, Miss Bella?
You will not. You will figure out which one you should use. So what domain do each of those x values satisfy, and then use that one rule to answer it.
All right, so you should just have one answer for x equals -1 and one answer for x equals 3. Okay, so now we're going to look at how to graph a piecewise function by graphing each piece of the function. So make sure you put this one in your notes. We're graphing g of x equaling 1/4 x plus 3 for x less than 0, and -2x plus 3 if x is greater than or equal to 0. So if we start off with this first part, really think of this as the line y equals 1/4 x plus 3. So we're really graphing the line that has a y-intercept at 3 and slope of 1/4. So I'm going to go up 1 to the right 4, up 1 to the right 4, and I get this line coming through like this. But I don't want the whole line. I only want the line for x's that are less than 0. So that means I am going to erase all of this and only keep this part right here. And I might even make this look a little bit neater. So like this, forward, down like this. So the graph looks like this. One thing to point out though, notice that x is not less than or equal to 0, it's strictly less than 0, which means we cannot include this point right here, so we indicate that by putting a hole in the graph. That means that you could take all the values up to that point, but not including that point 0, 3. There'd be a hole in the graph at 0, 3.
All right, let's do our second piece of this piecewise function. So it's going to be the equation y equals, if this helps us, -2x plus 3. And we're looking for when x is greater than or equal to 0. Again, kind of the mx plus b format. My y-intercept is at +3, and my slope will be -2. Well, if I make my intercept at +3, it's going to kind of fill in that hole that we just had created by the function in blue. So we'll start at 3, and my slope again was -2 or -2/1. So I'll move down 2, 1 to the right, down 2, 1 to the right, or I can go up 2, 1 to the left. Now I would draw in that function and that linear graph I have here. Now if we notice our restriction, x had to be greater than or equal to 0. So really, I don't want anything where x is less than 0. So I don't want any of these values to the left of the y-axis. I only want from 0 and greater, so only on the right-hand side. So those are my two piecewise functions there, and that is the graph of g of x. Both parts must be shown there. Okay, we're going to do one more. This one is also named g of x. Again, it has two pieces. And we're going to start by doing each restriction on its own. So we're going to start off with the first part of x squared minus 3 if x is less than 0. So if you notice, x squared minus 3 is a parabola. It is just like the parent function f of x, but it was shifted down 3 units, if that would help. Again, another option we always have, you can pick some x's and you can pick some y's of what this might be if you think of this as y equals. And I could put in 0, and that would be 0 squared minus 3, or -3. So my first point is 0, -3. Let's maybe make this graph a little bit bigger for us. And I'm going to put it right there, 0, -3. Again, since I know that that was a less than, I know right away it's going to have to be an open circle. So I'm going to put right away, make an open circle there. Now, something that might be helpful, we don't have a slope to count, is I might just pick some values of x that are less than 0 and put them in my table to get some points. So maybe let's try -1. -2, and -3, just to help me draw on this part of the graph. So -1 squared minus 3 will be 1 minus 3, or -2. So -1, -2. -2 squared minus 3 will be 4 minus 3, or +1. So -2, +1. And -3 squared minus 3 is 9 minus 3, or 6. So -3, 6. Again, it's a parabola, and we will draw it in, opening up, only when x is less than 0.
Okay, and then to get the other part of the graph, we are using the equation y equals 1/2 x minus 3. So it's just going to be a linear function with the y-intercept at -3. So again, that y-intercept, that point at 0, -3 is filling in that hole from the first function. And we have a slope of 1/2. So we're going up 1 to the right 2, up 1 to the right 2. down 1 to the left 2, down 1 to the left 2, but we really only want to see this graph between 0 and 4. So I'm going to get rid of any points that are not between 0 and 4, and it looks like I want just this piece of the graph here, and we're actually ending up with a hole in the graph, aren't we, Miss Bella?
We are.
All right, so that hole in the graph looks like it's right at 4, -1. So that would be our graph for this function.
I think one thing just to kind of point out, because both of these examples had it happen, it was just the examples that we picked that the hole in the graph from the first one was filled in by the point of the second one. So, I mean, you could have a graph, let's just, you could have a graph when you graph it that this piece maybe ends up here with a hole on this point, and this part doesn't pick up to down here and maybe goes this way. That's possible. They don't always have to fill each other in, but both of these examples just so happen to have that happen. All right, and I want to say that that's it. We're actually not going to do that last example. So that's the end of our 6.3 note. So thank you for watching.
All right, have a good day.